Hello everyone and welcome to another Stat 437 lecture video. In today's video we are going to be recapping everything that we talked about with longitudinal data throughout the term so far. So basically the point of today's lecture is to serve as a review for the first half of the material that we covered, which is everything to do with analyzing longitudinal data. And then after today's lecture, we're going to start talking about survival analysis, which is sort of the second half of the course. So with that, I'm just going to be sort of summarizing all of the topics that we covered, and hopefully this is all a review for you, but I'm hopeful that this can serve as sort of a good checklist for all of what we covered, all of what you should be taking away from this course, and that type of thing. So to begin, we can recap where we started, which was talking about what longitudinal data actually are. Right, so with longitudinal data, we're discussing repeated measurements over time. Right, and so this is in contrast to how we would normally think about a cross-sectional study, for instance, where we have multiple different groups of individuals at the same point in time. With longitudinal data, we follow a group or perhaps several groups throughout time, and we repeatedly take measurements that are of interest. Now, this is a unique structure for us to consider because that involves correlation within the subjects. So we don't have IID data at the actual observation level. Each subject is independent of all of the other subjects, but within each subject, there's also this correlation. And so because of that, our traditional methods sort of fall down when we're trying to use them. That means that we require special techniques to analyze them, which is of course what we've spent most of the term so far talking about. Now, in practice, from a practical perspective, we talked about how we can go from long to wide formatted data, and we've done that a bunch throughout the term. So hopefully you're familiar with that, but that's, one of the techniques of if you're going to be applying these techniques in the real world, you should feel comfortable sort of manipulating the data, and those are the common formats for us to store them. And we've also talked about how we have to be mindful of the time scale and whether or not the data are balanced. So what I mean by this is that we've looked at examples where we've used an individual's age as the time variable. We've looked at examples where it's been time since the start of the study. We've looked at examples where it's actually the time. And so because of this, we can think about longitudinal effects in any number of ways where it's not just time passing, but it's also what do we mean by time, right? And with balanced versus non-balanced data, remember that the key distinction there is that balanced data, everyone has measurements taken at the same points in time, and they all have the same number of measurements. It's nicer to work with balanced data, but in practice, we're often going to end up with imbalanced data, particularly when there's missingness. So after we sort of introduced broadly, we talked about marginal models or generalized linear marginal models. So these formed an extension of GLMs to longitudinal data, right? So we saw how you can set up using this link function and sort of a distributional assumption. We saw how we can take linear regression and turn it into generalized linear models. And with linear marginal models, it was the same idea. So we specify a link function, a variance function, and a correlation pattern, and that's all we need to do, right? So this is sort of non-parametric in the way that we're not talking about specific distributions, but oftentimes we're going to be informing these models from specific distributions, right? So if we have count data, for instance, we don't explicitly say that it has to be some sort of Poisson distribution, but we say in the univariate case, we would normally assume that this is going to be Poisson. And so we can take the link function, so the log in this case, the linear predictor, we can take the variance function where it's probably an over dispersed, but where the variance equals the mean. And then the correlation pattern, which we've seen can be unstructured, but if you have sort of enough parameters, the unstructured matrix becomes unruly, and then we need to start working from pattern matrices, right? So we've sort of informed the way that we specify these models through the use of generalized linear models. These models are fit at the population level, right? So they serve as the parameters serve as estimates for what happens on the whole over the whole population. So they're not at the individual level. And this is useful for us in terms of population level inference, but it does leave something to be desired that we'll need to sort of overcome afterwards. We talked about how we estimate them using generalized estimating equations, which we saw come out of estimation theory, right? And so this is how we can do the estimation without requiring distributional specification, okay? And so because of that, we get asymptotic normality, we get consistency, we get valid estimators without actually needing to say what the distribution is specifically. And when we do specify the distribution specifically, for instance, in the continuous case, where we might specify that it's normally distributed, in that case, these become likelihood-based techniques, right? So they're quasi-likelihood or pseudo-likelihood techniques, and they work effectively given this sort of limited specification for the model. So in the continuous case, we saw the likelihood alternative, and I'll just point out again that this is sort of the exact same thing that you saw with linear regression, right? So in regression, you can think about assuming that the errors are normally distributed, which gives you some nice efficiency properties and some nice small sample properties. But if you don't want to make the normality assumption, then we can also say in the case where we're not assuming normality, we can still use sort of least squares estimation to have valid estimators that look identical. So this is essentially the same concept except for longitudinal models. In terms of estimation via R programming, we saw that we could use the GLS function from the NLME package, or we can use the GEE-GLM. And both of these sort of extend what we would expect from linear models or generalized linear models in terms of their specification. And so they should be quite familiar to specify, but you just need to add in the additional bits that you're not normally requiring, like the variance function or the correlation function as well. So after we talked about marginal models, we talked about mixed effects models, right? And so the idea was take the limitations from a marginal model, transform them to linear mixed effects models. So the key limitation is that a marginal model can't estimate or individual level effects. And so in the linear mixed effects models, we try to find a way to estimate both the individual effects and the population level effects. And so the way that they do this is they account for correlation by adding what we call random effects terms, which essentially is going to be additional terms that are specific to the individual, right? And so we end up imposing a distribution on those. And by doing this, we can generate whatever correlation structure we want, but this is by explicitly modeling where these correlations come from. So we specify the full distribution for these random effects terms, and we're sort of explicitly modeling the entire structure of the process. So instead of just saying that there's going to be some correlation within an individual, we're saying this correlation comes because there's some effect on each individual on their time variable or on the age variable or on their height or whatever the case may be. And then because that's an effect that's specific to the individual, every one of their measurements is sort of going to be biased off of the population mean in the same direction. And that's going to impose this correlation. Because it's a full distributional technique, we require likelihood theory to fit it, right? So we've actually assumed a complete distribution, and then we can use maximum likelihood to do it. The drawback to doing this is that, of course, if you get the distribution incorrectly specified, the estimates are not going to be valid, which is not the case with marginal models. If you misspecify something there, then as long as the mean structure is still correct, you get consistent estimation. In R, we're going to be using the NLME package, and it's the LME function. And again, behaves more or less like you would expect from a GLM. The biggest difference there is you have to specifically specify your fixed effects terms and your random effects terms. After linear mixed effects models, we discussed transition models. And transition models were sort of a reframing of the problem entirely to draw on stochastic processes. And they were most easily motivated through the use of categorical data. So if you have categorical longitudinal data, you can think about this as a stochastic process where individuals are transitioning between states over time. And then if that's how you're conceptualizing the longitudinal data, well then the correlation that we're observing comes through this process, and all that we need to do is sort of indicate the transition probabilities. So we talked about the Markov assumptions or the time homogeneity assumptions, right? And the idea here is that with the Markov assumption, only the last R states matter, right? Anything before R time units ago does not factor into our decision at all. And with time homogeneity, the idea is that it doesn't matter what time we're looking at the process, the transition probabilities are going to be the same, right? And so these were just simplifying assumptions, but with the Markov assumption in particular, that lets us sort of parsimoniously model these data. We can fit this using a likelihood procedure without covariates, and that just let us sort of make our estimates based on summary tables of the data, right? If we knew how many transitions were going between the states at the different times, then that lets us estimate this through a maximum likelihood. And if we wanted to include other covariates to sort of modify those transition probabilities, we can do that using standard GLM. In R, in order to estimate them then, we can make use of the table function, which just summarizes the transition counts, or we can use the GLM function. And we're going to need to create the correct lagged series and whatnot and set up our data to be exactly right with that. But overall, they're using sort of those standard built-in tools. After we introduced transition models, we've most recently been talking about missing data, which is a pervasive problem. So oftentimes, longitudinal data in particular are subject to quite severe missingness. We talked about how the missingness can sort of follow one of three different hierarchical structures. So we have missing completely at random, where with missing completely at random, the missingness does not depend on the observations at all, right? So it's just totally random. And that's the best way that missingness can occur because we can just keep using the available data and it will work. It's going to produce unbiased, consistent results. One step beyond missing completely at random is missing at random. And with missing at random data, it depends on the observations, on the outcomes that are going to be missing, but it only depends on what we've observed. So at time point 1, that might inform the missingness at time point 2, but the value at time point 2 that's missing does not predict the missingness itself. And with missing at random data, we saw that we can start to address these concerns, and so they're not so bad, but they do require a little bit more work. And then we have not missing at random data, and this is where the missing value itself is predictive of whether or not you are missing, right? So higher values are more likely to be missing, for instance. In the case of not missing at random data, we can't address it without explicitly modeling the missingness problem. And so because of that, it's sort of the least ideal situation for missingness. It's easier to handle missingness when we have monotone missing patterns. So for instance, using dropout. And what we mean by that is that we want to be able to order the data frame such that once someone is missing, they're sort of no longer going to be observed ever again. So we get that nice monotone structure. And the reason that we like that is that when we're going to do something like imputation, it means that we can always work from a stable set of covariates and then impute the next one. And then there's sort of fully observed and then impute the next one and so forth. We can use weighting techniques or imputation to account for the missingness. So we talked about sort of the inverse probability weighting, where you say what is the likelihood that someone is still in the sample after a given point, and then weight them inversely proportional to that. And that creates this pseudo population, which will be unbiased for the true estimates. And then with imputation, the idea is we fit models to predict what those values would have been. We do this a bunch of times to account for the uncertainty that is inherent in that process. And by doing so, if we get our models correct, that will correct for the missingness. But both of these techniques are only suitable when we're talking about missing at random data. And we also saw that, or we also stated that likelihood procedures are a type of imputation technique, essentially. And there are ways of formalizing that a little bit more through expectation maximization or similar. In R, we looked at using the mice package and the mice function in particular for doing imputation. And we looked at just using GLM in R to end up using our weighting techniques. And so that's longitudinal data in a nutshell. Obviously, there's a lot more that we could be talking about in terms of this. We could dive deeper into any one of these topics. You could work out the theory more deeply. You could look at other forms of marginal models or other forms of mixed effects models. There's stuff from the economics literature that deals with this as well. But that gives you sort of a very, you know, uh, thorough overview of the types of techniques that people are likely to be applying to these data. And it also sort of lets you think a little bit critically about how we're going to be able to analyze these. So even if you see a new technique in the future that's going to be analyzing longitudinal data, you sort of know they're going to be accounting for the correlation structure somewhere. And how they choose to do that is going to dictate sort of the constraints of the model, right? So if they're explicitly modeling what that correlation structure is, then you might be able to get out some individual level effects, but you're probably going to have to give up something in terms of your models have to be correct, right? And this is going to be true across the board. And hopefully that sort of gives you a nice framework for working within. So the question is, what is coming next? And we're going to learn how to analyze survival data. So this is not completely distinct from longitudinal data. Survival data is a particular kind of longitudinal data, but it has its own techniques, its own quirks. There's sort of a different area of focus. And so I hope that this has been sort of a good, useful overview of longitudinal data for you, that you feel more comfortable working with these techniques. And, of course, you'll get more practice of this throughout the rest of the term. If you have any questions on anything that we've talked about within longitudinal data at all, please reach out from any point throughout the term so far. And, I'll see you in the next lecture video where we begin to talk about the analysis of survival data.